I'm going to do three examples from chapter 18. So starting with number 32, which talks about museum membership. A museum offers several levels of a membership as shown in the table. So we've got the individual, and then they tell us, the different member categories. They tell us how much it costs for that and the percent of the members that do that, they choose that. If you add up the percent of the members, this adds up to 100%. So the first question we're asked is to find the mean and standard deviation of the donations. So to find the mean of this goes back to the probability distribution charts that we did. So for part A, to find the mean or the expected value, so this would be mu sub x is what I might call this, we're going to take 50 times 0.41 plus 100 times 0.37, continue that, and then 1,000 times 0.01, and then see what we get. So this is how we would do it by hand, or we could use our calculator. We could type in the amount of donations into L1, the percentages into L2, and then what we're going to do is stat, calc, one variable stats, L1 and L2 is our list and frequency list. And then when we calculate that, we get 137, and this would be dollars. So $137.50, which is what you would get by hand. And we do this on the calculator because it's so much easier to find our standard deviation, which in this case is going to be $148.56. So that's what we could do for the first part to find the mean and standard deviation of the donations. Nothing new here. Part B asks, during their annual membership drive, they hope to sign up 50 new members each day. Would you expect the distribution of the donations for a day to follow a normal model? Explain. Now, we're taking a sample size of 50, so 50 new members. But the question in part B is only asking us about one particular day. So would you expect it to follow a normal model? No. And the reason why is we're just talking about one particular day. I would expect that day to kind of follow this up here. So I would expect maybe 41% of the people would choose the individual plan. I probably won't even get a benefactor out of only 50. I might, but there's a good chance I won't get one of those because it's so unlikely to get a benefactor. So I'm not expecting that because it's more likely it will more likely follow the population distribution, since it's only one day. Okay, so we're only looking at one day. Now, part C is where we get into our new material. Consider the mean donation of the 50 new members each day. Describe the sampling model for these means. So now it's like, okay, we have 50 new members a day, for one day, and then 50 new members the next day, 50 new members the next day. So we're looking at lots of sample means. So every time we take a sample of 50, we get an X bar value. So this now we're looking at the sampling, we're looking at the distribution. This is looking at the distribution of all the X bar values of size 50 that we go through, again and again. So that's why B was different. Part B was only asking for one particular X bar value. This is looking at the distribution of all the values. So at this point, we have to look at our conditions. So I gave you that paper that talks about the sampling distribution models and the conditions. So I'm not going to recopy these. I just want to go through and talk about them. The randomization condition. The members are not selected randomly. We're not told that. They're simply the new members that day. So we have to be able to assume that the donations that those people make are typical of the donations made by current members, that it's representative of the population. And you could say it that way. You could say the members are not randomly selected, so we're assuming that the donations are typical or are representative of the population. Then this idea of the independence assumption. Now remember what I told you in class, these two things kind of go together. We are not sampling with replacement. So although they go and make this statement that they think, okay, well, probably the new members, the donations are not going to affect one another, like what one person chooses is not going to really affect what another person chooses. But if you left this part out, that's okay. Just don't leave out the next part, the 10% condition. The 50 donations represent less than 10% of all donations. Or you can even talk about like the 50 new memberships, represent less than 10% of all of the memberships. And large enough sample condition, the sample of 50 donations is large enough. Now remember what I told you, I said N is greater than 40 is kind of our threshold amount that we're looking at. And since 50 satisfies that, it's large enough. So remember we've got randomization, large enough but not too large are our three ideas. And this 10% condition is really the same as our independence part. So because the conditions are met, so conditions are met, so we can say that our sampling distribution of the sample means is approximately normal with mean mu sub x. So our mean is mu sub x, which is, well, let's call it mu sub x bar, which is the same as mu sub x. So it's going to be $137.50. And standard deviation. So our standard deviation for our x bars is going to be sigma x divided by the square root of n. So in this case, it's $148.56 divided by the square root of 50 because we're doing 50 is our sample size. So we can calculate this, and I get $21.01. So look how much smaller my standard deviation is. So it's approximately normal with a mean of $137.50 and a standard deviation of $21.01. So notice my approximately normal. Okay, that's important because our population was not normal. So when we do our sampling distribution, we can just say it's approximately normal. Now, they don't ask us to do anything with this value. We were just asked to describe the sampling model, shape, center, and spread. The shape is approximately normal. The center is $137.50. The spread is $21.01. So that's my shape, center, and spread. I'm describing it with my normal model here. All right, so problem 34, still talking about the museum. One of the museum's phone volunteers sets a personal goal of getting an average donation of at least $100 from the new members she enrolls during the membership drive. If she gets 80 new members, and they can be considered a random sample of all the museum's members, what's the probability that she can achieve her goal? So our sample size for this problem is now 80. Instead of 50, it's 80. And she is wanting to know the probability that her average donation can be at least $100. Now, when we are dealing with normal distributions, whether or not you do greater than or equal to or just strictly greater than doesn't matter, like it did for binomial and geometric. So in this case, it's okay if you just do greater than 100. If you put the or equal to, that would be okay as well. So looking at my conditions, because I have a new sample size, so I would need to check my conditions again. So we are told it's a random sample, or we can consider, she said considered a random sample. So we're told we can consider it that. Our 10% rule, so we are going to assume that 80 is less than 10% of all new members, you know, over a period of time, the different members. And our third thing we should mention is n is greater than 40. So sample size is large enough. Now, if you want, you can say it seems reasonable that the new members would be independent of each other. But again, that's the reason why we have this rule here, that that it's less than 10% of all new members. We are sampling without replacement, so that's why we have that there. So once you do that, then we can say it's approximately normal with a mean. Now our mean is going to be exactly the same thing as it was before. So our mean is still $137.50 because we still have our same population. So it's going to be $137 and I already forgot, 50 cents. But our standard deviation is going to be different because to get our standard deviation, we take our population standard deviation, and divide by the square root of n, and we changed n. So every time you change n, you change that standard deviation. So we're going to have 148.56 divided by the square root of 80. So I get about $16.61. So now this is my distribution, but now they ask me a question. What's the probability that she can achieve her goal? And her goal was that she would get more than 100. So we want to know the probability that her X bar value from her sample is greater than or equal to 100. So we have this normal model, and I'm going to place my 137.50. Since my 100 is going to be below that, I'm going to just count this way. So if I take 137.50 and subtract 16.61, so I have 120.89. Do that again, and I get 104.28. One more time, and we have 87.67. So my 100 somewhere in here. So meeting her goal looks like this. Now this is my supporting work because I'm choosing to do normal CDF. My lower bound is going to be 100. My upper bound, something ridiculously high. My mean, and my standard deviation. So again, your picture is pretty crucial there. So normal CDF, and we're going to have 100. I'll put in 10 to the 99th power. My mean, 137.50. My standard deviation, and I get 0.9880. So what's the probability she can achieve her goal? I'd say it's pretty likely. So the last one I want to do, number 36, is about potato chips. The weight of potato chips in a medium-sized bag is stated to be 10 ounces. The amount that the packaging machine puts in these bags is believed to have a normal model with mean 10.2 ounces, and standard deviation 0.12 ounces. Now, that's what I do. When I'm reading a problem and I see that, I just write that down. Now, this is different. Remember in the preceding problem we did, our population was not normal. This was definitely skewed. It's all bunched up at the individual and some family and tapers off, so it's definitely skewed to those higher dollar amount donations. But now we're told that it's normal. So the difference, what that means is, whereas here we had to say that if the conditions were met, it was approximately normal. Now it's exactly normal. So on this problem, so because our parent population is normal, then any sampling distributions from that are also normal. It also means I don't have to have n is greater than 40 to use these techniques, because I can still use a normal model even for smaller sample sizes. So part A says, what fraction of all bags sold are underweight? So for this, we are just using our regular old normal model. So here's 10.2. Since it's underweight, I'm going to go this direction. And if we take 10.2 minus 0.12, I get 10. Oh, what did I do? Oh, that's right. Minus 0.12 again. Okay, so now I have 9.96. If it's underweight, think about what that means. They are stating that there's 10 ounces in the bag. So to be underweight means I'm looking at the proportion of bags that are less than 10 ounces. Now notice my symbol. I didn't put an X bar. I'm not talking about a sample mean. I'm talking about just in general the bags. If I take a bag at random, what's the probability that it's going to be underweight? So this just X. So then I would be looking at something like this. So I could do normal CDF. I'm not going to write all that down. But if we do normal CDF, and my lower bound is negative 10 to the 99, something very small. My upper bound is 10. My mean is 10.2. My standard deviation is 0.12. And I get for an answer 0.0478. So that would be the probability of having a bag underweight. I guess you might look at that, it doesn't have to be like a fraction. It can just be like a percentage, or just what part of all the bags sold are underweight. So then in part B, it says some of the chips are sold in bargain packs of 3 bags. What's the probability that none of the 3 is underweight? None is underweight. So that means the first one is not underweight. So let's think about that. The probability of being underweight, probably none of the 3 is underweight. So the probability of being underweight, I don't need to do that. I'll just write it this, none underweight. So let's think about the probability that if this is the probability it's underweight, then not being underweight would be 0.9521. And if none of them are underweight, then that would be times that to the 3rd power. So if this is the probability a bag is underweight, then subtract that from 1 to get the probability that the bag is not underweight. And then I want none of the 3 underweight. So that means the first one's not, the second one's not, and the third one's not. Assuming that they are independent, I can multiply them together. So this is just like what we did in our last unit on probability. So I get 0.8631. And that would be my answer, that none of them are underweight. Part C says, what's the probability that the mean weight of the 3 bags is below the stated amount? So now it's saying what's the probability that it's some mean, it's an X bar value, is less than the stated amount. And we have this with our sample of where n is 3 because we have 3 bags. And I want to know the mean weight less than 10. Now all of a sudden I'm looking at a sampling distribution. So this is our new material. Before I can answer this question, I have to check conditions. And rather than write them down, I just copied it here and I want to talk about them. So randomization assumed that the 3 bags can be considered a representative sample of all the bags because we don't necessarily have anything about randomizing it. So we're just going to have to make that assumption that the 3 bags are representative of all the bags. Again, independence and the 10% condition kind of go together. We're sampling without replacement, so we have to make sure that our 3 bags are less than 10% of all bags, which of course they would be. There's a lot more bags than 30 bags of chips that are manufactured. And then our large enough sample condition, because the population distribution is normal, then 3 bags is large enough. We don't have to be greater than 40. So you're going to have to remember that. If the parent population is normal, they tell you it's stated normal, then n can be any size, and that part doesn't matter. So if our conditions are met, we can go on, and so I'm just going to say conditions met. So that means my distribution is approximately, nope, it's normal. I don't need the approximation, and I don't want to use it if that's not appropriate here. It's normal with a mean of 10.2 and a standard deviation of 0.12 divided by the square root of 3. You can write it like that. Remember that it's the standard deviation of the population divided by the square root of n. That's the formula I'm using. So that's why I had 0.12 over the square root of 3. And I want to know what's the probability the mean weight of the bags is below 10. So we can do this again. Actually, we have to do this again. And now I'm going to figure out 0.12 divided by the square root of 3. So this is 0.0693. So if I take 10, and I have, we'll call this 9.93. Oh wait, sorry, messed up. 10.2. So we have 10.13, 10.06, 9.99. So 10 is about here. So the probability of it being underweight, and again, if I do normal CDF, my lower bound, negative 10 to the 99. I think I had that in there, didn't I? My upper bound, my mean, the only thing that changes is my standard deviation. I'm going to put 0.0693. Don't just round it to 0.07. At least go 4 places, or else type in 0.12 divided by the square root of 3. That's even better. And so now I see that my answer is 0.0020 if I round to that place. Now, that's the probability that I would get a sample mean of those 3 bags less than 10. So remember that the probability of a bag being underweight was almost 5%, but the probability of the mean with just 3 bags is much, much smaller. So then they ask in part D, what's the probability that the mean weight of a 24 bag case of potato chips is below 10 ounces? So I'm still answering this question. it's still the sample mean. It's still what's the probability that X bar is less than 10. But now N has changed, and now N is 24. So as long as conditions are still met, which would just be an issue of is this still less than 10% of all the bags, which yes it is. So now when I calculate this, my mean is still going to be the same, 10.2. My standard deviation is going to change. Now it's going to be 0.12 divided by the square root of 24, so it's going to be smaller. So if we calculate that and we get 0.12 divided by the square root of 24, I get a normal model, mean of 10.2, standard deviation of 0.0245. And I'm not going to draw the whole picture out again. I'm just going to calculate this. If we do second distribution, left bound is still going to be the same. My upper bound is going to be the same. Mean is the same, but my standard deviation is 0.0245. And so when I calculate this one, I get basically 0. My calculator just says, oh, we can't go that low, and it says 0. So virtually it's impossible. Now this is important because what if I did take a sample of 24 bags and I got a sample mean less than 10? That would tell me something. It would tell me that the mean weight was not really 10.2. And it would tell me that my machine was not filling them full enough. So that's why this is important, what we're doing, and looking at the distribution of the sample mean. So hopefully that helps, and that's it.